So our next speaker this afternoon is Stephen Batish from Microsoft. Stephen leads Microsoft's Applied Science Group, an interdisciplinary team of scientists, AI researchers, and product engineers in the Windows and Devices organization. His expertise lies in multidisciplinary approaches, a broad range of sciences and engineering, display technology, sensing technology, algorithms, and software. He's been shipping and inventing new Microsoft devices, interfaces, and experiences since 1999, from conceptualizing the original Surface tablet in 2001 to contributing key innovations to the present line of tablets, laptops, and entirely new form factors. He has helped evolve the PC architecture with neural processors, built AI experiences in Windows, and developed foundational AI devices. He holds more than 120 patents and has been awarded several honors of distinction, including being named a Fellow of the Society for Information Display and being honored as an innovator by the IEEE. He is a frequent speaker at international conferences, distinguished lecturer, and his work has been featured in both technical publications and popular media. I am pleased to welcome Stephen Batish.
Thank you, Steve. That was lovely. Just wanted to do a quick sound check. Can everyone hear me? I can't see anyone in the room. I wish I could. But all's good, right?
Yes,
Okay.
you're
Thank
good.
You. Perfect. All right. Thank you so much. Sorry, folks, I couldn't be there. I'm managing multiple conferences at the same time and trying to split my time. But I really appreciate everyone here for making this work. Really excited to share some of the work we've been doing over the past few years. Really thankful for Steve Atwood and Adrian Travis asking me to come speak at this wonderful prophecy event to think about how things might look like in the future. One of the theme of my talk is the dawn of computer-aided reasoning and what it potentially means to human-computer interfaces. I'll use real examples today and how it is affecting how we work and communicate in the future, and potentially how it's going to affect our displays and interfaces moving forward. First, computers are really good these days at telling the difference between dogs and cats. And we do this using a neural network. We can train an algorithm that is multi-layer, and it's a dense neural network that is typically treated as a black box. The values of those images flow through the network. They're being weighted and summed along the way until it gets to the final layer where the relevant output neuron is essentially voted upon. Each of those lines and circles represent some level of computation, and there are a lot of them, and that's kind of the important point here. Networks these days have millions, if not billions, of these connections, and now compute is measured in units of gigamax, or billions and billions of multiplies and accumulates. It's pretty crazy. If you look at how we compute these this new algorithm type, you look at our processors available to us. You have the CPUs, which were honestly really designed to multiply two numbers together. And they do that really well, really efficiently. GPUs came along, and they're really good at computing arrays, as you can see here. And there's a new processor class evolving. It's been evolving for a number of years now called the neural processing unit. And several people call it different names. But it's really good. Nevertheless, it does one thing really well, and that is essentially multiplying tensors or arrays of arrays to do that. And they employ all sorts of techniques and tricks to essentially do that efficiently, especially in mobile devices. They pipeline things using memory bandwidth because you want to keep essentially your compute processors busy. There's interesting architectures that are challenging the traditional binomial compute architectures, where we're doing spatial memory layouts, where we're putting essentially data right next to the compute architectures, and that provides a lot of efficiencies. Believe it or not, most of the penalties and energetics inside a PC is moving data around, not necessarily the actual math involved. These neural processors are really good at doing high parallel compute units, and they have even specific implementations of the math operations, dedicated processors, if you will. As a result, a lot of the the speed that you're seeing in today's computers isn't necessarily attributed to Moore's law as much as it is attributed to these domain-specific architectures and innovations, and that's pretty exciting. If I give you a bar graph here to kind of illustrate a point, on the y-axis you have basically total compute load in teramax. On the x-axis here you have compute efficiency, and we talk about it. We think about it teramax per second per watt, and think of that as on the y-axis this is like how fast a car can go, and then on the x-axis what's the gas mileage. And GPUs are really good at really high horsepower, but you can tell they're not very efficient. I mean, you can see that today. I mean, it kind of just makes sense. GPUs, not even in data centers, and in your computers, they operate in an envelope of many tens to hundreds of watts, where these neural processing units are really trying to aim for the sub 10 watt range and delivering some pretty impressive compute abilities. I'll give you an example. These are real examples that my team's working on. These on this graph here at the bottom are actual AI experiences that we're working on, are already shipped in Windows or are going to ship in Windows. Head pose tracker, eye contact, face detector, and segmentation. If we actually put those up, take those same algorithms, optimize them as best we can for those specific processors, the GPU, the CPU, and the NPU, and just kind of compare how much, how fast essentially they can run, which is an estimate of actually the efficiency of it. You can see that the neural processing unit is extremely powerful, extremely fast. And if that graph is not impressive alone, just put in perspective, that CPU is running at 65 watts and it's over $100. That GPU is really easily running at 120 watts and it's easily more than $150. But that little NPU on the die is $5 and operates under a 5-watt envelope. That is the revolution that is occurring in our industry. And what that allows us to do is put compute local right there where you need it, and it's going to be highly efficient, and you're going to be able to do things that weren't possible before because it would tax the CPU or GPU too much, or it would essentially suck up your battery. And so now we're entering this new age of massive abilities, and it's going to have amazing applicability across human-computer interfaces, how we do productivity, telepresence, computational photography, and even security, privacy, and trust. So let's look at some examples of telepresence and computational photography. I've spoken a few times here at SID, and everyone's known kind of this vision that I've been talking about, the magic window, this thing that brings together people as if they're in the same room, either done through fancy transparent screens and multiple camera arrays or high computational abilities. Let's talk about the transparent screens, which are really exciting work. This class of device in technology has enabled us to put cameras behind a screen. It allows us to put cameras hidden in our cell phones. Here's some work my team has just published around using AI processing, local AI processing, to recover the image that would typically be muddled by looking through that pixelated, essentially, display. A perfect example of AI being applied currently today to do these sorts of computational photography needs. And there's far more examples in the mobile phone space. A lot of the beautiful pictures that you see today is attributed to AI running locally on those devices. You can take multiple cameras together and stitch them together to interpolate and create a multi-camera synthesis through a transparent OLED. Here you see Neil being able to look around Neil, which is pretty cool. We can do it to do eye contact, where you actually have the cameras physically right behind the image that you're looking at, so that where you're looking at is the same place that that person is looking through, which is pretty cool. We can use AI here in these situations also to scale people appropriately. So when you're doing the person-to-person communication, they're neither too large nor too small, which often happens in video conferencing sessions. I'm sure I'm quite small on your screen right now. So this is Sihun in a smaller form talking to Neil, or I would say life-size form talking to Neil. Putting all that together allows us to do, obviously, some of these magic window scenarios. Here's a transparent screen, a multiple camera array system, and allowing people to essentially collaborate together as if they were in the same whiteboard in a room. Speaking of whiteboards, one of the things that we've been pushing for quite some time is a Microsoft Service Hub, a really amazing telepresence tool. My team just shipped a really novel AI camera that is an example of this new device class that you will see more and more of. This device class has AI compute, tremendous actually AI compute embedded into it to do better telepresence and teleconferencing needs. So we just launched this. This is the camera running in real time. You're in a conference room. It has a 180-degree field of view. And locally, to do that and not lose pixels, you need 12 megapixels. So that's a lot of data pixels to essentially shuttle the PC. You can't really do that. Therefore, you have to process locally. And in order to process locally, you have to have the person detectors running locally. And even the software to do the auto framing running locally. And that's what you hear. We designed a pretty awesome piece of optic, 12 megapixels, has a massive depth of field, so it can image near to far, an innovative dewarp mechanism that is actually also embedded directly in the cameras. And like I said, there's 1 teraflop of compute running under a 5-watt envelope inside this device to do all that processing in real time. Here's an example of the dewarp, which kind of makes using dewarp techniques to make it look like the camera is coming through the screen. Watch this. This is the camera not actually physically moving, but it's literally fixing the distortions that you get by having the camera up high and the wide and the fisheye lens. And this is the algorithm running inside the camera itself, doing the face and body detections, whether you're looking at the camera or facing it towards, it operates really efficiently. I show you this as an example of a device that is kind of emerging. It is out there in the real world, but you will see more and more of these sorts of things in the wild, and they'll do more and more things. This is just the beginning, doing this cinematic director experience. Now let's talk about what's happening in the PC world, Windows plus the devices. Some of the things that is enabled by putting the neural processing units inside these devices, what we can start doing, and potentially what we can be doing in the future. So here is a cloud quality face tracker, extremely robust. The beauty about this face tracker that's now shipping in these Pro X devices is no matter whether you're wearing glasses, you're wearing a mask, you're partially occluded, or you turn down the lights, you have an amazing level of robustness that is quite important to maintain, or whether you're walking really far away. That's really helpful when you're trying to do auto exposure to make these systems essentially do better video quality. Here you have eye contact that is also shipping in the Pro X, you can see here that the eyes are actually shifted automatically. So we didn't use a transparent screen in the Pro X. We used computation to solve for where the eyes are looking at, so you can have this eye-to-eye contact. Again, the beauty about all this is that the algorithm, that face detector that we placed in Windows, the new one that's so powerful, it actually consumes less power than the old one. The eye contact barely consumes much power at all. Here we can use it to do eye tracking without fancy 3D cameras. Now, of course, the resolution that we can resolve isn't on the word level, but you can think of it as it's kind of zones across the screen to help the computer understand where you're essentially looking at. Exciting things is, even in low bandwidth situations, or when you're trying to conserve power, maybe you want to send a low bandwidth line, and on the receiving side, actually do super resolution to up resolution the image and have it be high quality, which is exciting. You can see this a lot in what's happening, for example, in our gaming division in Xbox. Xbox does essentially 4K, but believe it or not, a lot of the computation is done sub 4K and then up resolution using these AI algorithms at the last stage. to get the 4K quality, which is pretty amazing. Here, we kind of futuristic stuff is we can use these AI algorithms running these devices to make people look like they're more frontal parallel and actually make the entire body shift. And this is not using any fancy camera. This is the built-in camera that you see in our devices. Some pretty exciting things as well is real-time translation, connecting people across countries and barriers and languages. Here, this person is going to speak English, and we want the translation to happen in real time. But the problem is the lips don't follow that translation. But check this out. With AI, we can solve this problem.
But conservative activists insist he won't be able to move into the national limelight.
안녕하세요. 만나서 반가워요.
So that is all in real time. You can see we're using, we're essentially modifying the lips in coordination with the audio that's coming out from the translated voice. Now let's move on to examples in human-computer interfaces, especially Ink. Ink is an amazing way for people to express their ideas and thoughts. It's highly spatial, highly nonlinear, but honestly today it's still quite nascent. And it's nascent because we don't really have a very sophisticated algorithms yet to kind of make use of the messiness that's created with Ink, but that's going to change with AI. Here's an example. This is my team actually wrote a beautiful journal taking application. It's called Journal. You can download it today. You can see the link up there, aka.ms, get journal, download it, play with it. It is local AI running on your device to enable some pretty cool experiences. What it does is it does its best, one of the best applications that are out there to make sense of what text is, what pictures are, being able to select and circle things quite easily. An example of the use of AI, you can see there, the pen button has always been used to essentially, as a modifier to essentially, I want to select this group of things because the computer has never been smart enough to tell the difference. Here, we're not using the pen button. We're actually, you can see it in the next thing, we're actually in real time detecting the difference. You're trying to circle something, or are you trying to selection, or are you trying to circle something because that you want to actually draw a real circle. That is all without the use of a modern modifier button. That's magic happening in the background, and it is a perfect example of how things will look like and feel like in the future. Computers really understanding your intent rather than you being so explicit with your actions and being so programmatic, and that's exciting things. And that leads us to my last bit of my talk about large-scale AI, potentially one of the most exciting things happening in the AI field. One thing that's been clear, bigger is better. Larger and more complex models are doing human parity level tasks, human parity level reasoning, and in often cases actually exceeding human parity. These models, as you can see, has been steadily growing over every year. And the more they grow, the more compute they demand. Of course, we're talking about billions of parameters and hundreds of billions of parameters, essentially. And here's an example of a trillion parameter model. And these models are capable of doing some pretty extraordinary things. I'm going to show you real life examples of what's happening in Office that we're doing and actually is shipping or going to be shipping soon these days. Here, simple natural language using transformer models to predict what you're about to write and helping you complete. On the left is kind of the old way. On the right is the exciting, big, large-scale AI way. And you can see how quickly someone's able to kind of complete their thoughts and how accurate it is in predicting what this person wants to say. And that is pretty phenomenal, very magical. And again, kind of indicative of how things are going to evolve in the future, almost to the point where you can actually use AI to just write the paragraph for you. And in fact, we have examples there where it just does that. Solving riddles, you would think like, wait a minute, okay, so here's a riddle. all of us have one, but few of us get to choose. If you don't know my name, if you don't know mine, you're not my friend. When it is called, our attention is drawn. Even if you're gone, they are still around. And you give this to the large scale AI model, and you ask it to essentially solve it. Not only does it solve it with the right answer, the answer is name. It gives you the reason why it thinks it's name. A name, so it kind of completes it for you. So pretty phenomenal. I'm not going to bury the slide, but it's pretty amazing stuff. Another thing is kind of this mixed modality search, using images to find things, and then mixing it with text. So check this out. So here we have Brady, and you ask for a picture of the Patriots, or you want them in the picture of the Packers. Pretty nifty stuff there. So basically the summation of a picture plus a qualifier. Let's say I want a picture of the Eiffel Tower and I want it in Paris, or in context of Paris. It's pretty cool. And you want it as a sketch, or without a sketch, sorry, only photographs. And this is all real stuff happening. This is going to be available for people to use and play with in their productivity tasks, and it's going to be pretty amazing as a result of that. And if you like think a little bit, it's like, okay, if I take some of this, human parody sort of things happening and maybe combine it even with ink, I can start doing things like, guessing what a person's about to draw and help them complete the drawing, make people experts even though they weren't, or just take kind of a loose description of what you want and give you an image. I could use drawings to essentially search for things or kind of complete things. And you can see that as an example. So one of the big AI programs we have is in collaboration with OpenAI and DALL-E. So I took these literally just yesterday. I went and I used DALL-E. There's a website, and you type in these descriptive words, and it creates an image completely original for you as based on the words, and it's magical. And it's not like it searches the web and says, I want this, and put it together. It literally just imagines what it should draw just from the words that you're given. So for example, I typed in Winston Churchill in a Mona Lisa painting, and this is, I kid you not, this is the image it brought back to me, which is crazy. And it's a real image. A stern-looking owl dressed as a librarian as digital art. And this is the image that it brought back to me. And this is completely original. You will not find a picture of this anywhere else in the world. This is a complete original piece of art. A bowl of soup that looks like a monster knitted out of wool. And there you go. A little funny. I don't know why you would want that picture, but it is pretty freaky or amazing to think that computers can do these things today, and it's just a tip of the iceberg on how it's going to essentially affect our devices moving forward. And that's because I think one of my first talks that I give at SID, I talked about how important new display technologies and new interaction paradigms are the key ingredients for the creation of new computing form factors. Well, AI is going to change how we're able to interact with computers. Computers, you won't need to essentially be so explicit, so programmatic. You won't have to actually move your mouse to the specific pixel on the screen and double click on that icon to launch an application so you can hard code or hard type the words. It's going to be much more fuzzy, much more implicit. It's going to understand and reason more what you want to do, and build on top of other people's ideas, or even other AI's ideas, to essentially complete your tasks. I mean, this world that we're going to enter in is going to be mind-blowing. It's gonna look quite different than what you expect today. It's going to help you in ways that you never thought before. So that kind of leaves with kind of an important question for us here at SID. How will computers look like in the next 60 years? And like I said, for sure, I know data is maybe a cliche, and I don't think we're going to have androids in 60 years that do this, or maybe, but certainly we'll have behaviors in our computers where things will be able to essentially intuit and reason on the things we want. I'll ask my AI, can you please do a presentation for me for SID 2020 and take all my AI work that we've done in the past and put them together, and it'll actually do that rather than me manually creating it. Or I'll ask it, can you please make this diagram much nicer looking, and it'll just do that. And you already see examples of that. But I guess maybe the question that all of you are sitting there asking, if computers might look more like Android, what does that mean for our displays? And I would just say, fear not, even a century or half century from now, they still had tricorders, they still had displays. It's still necessary. We will need them, I promise, but they'll be used quite differently. Anyways, thank you so much for your attention. I really appreciate your time. I think I might be able to, I definitely have time to answer questions if folks want to. I don't know how we're going to relay them to me, but I'm here to listen.
Well, we do have a couple microphones. That was wonderful. We do have a couple of microphones set up if someone wants to ask a question. You had me with any sort of Star Trek references.
That's great.
Yeah.
I always win over, it's easy to win over fans that way.
Well, actually, if I can ask you, is how far away are we from my being able to describe a plot in a Star Trek story or Star Trek character universe and have it create the entire movie for me?
You are not far away from that, my friend. I will tell you this. So we have an exciting model that we're working on called Github Co-Pilot. And just an example, and it's real. It's a service that we currently run today. And what we did is GitHub is essentially the repository for code. It's massive, lots of code examples. And we trained a large-scale model on code. We basically taught an AI model how to code. And using essentially a loose level or English language, a developer can generate code using that model. And using, which is pretty amazing. I can literally ask it, write me a program that does food, and it'll go do that for the most part. This is like Gen 1, so, but, for sure, there'll be more and more sophisticated things in the future. But no doubt, using models like GPT-3, GPT-3 2.5, et cetera, moving forward, Turing NLG, you will be able to write a loose level description and it will actually create that storyline for you. And what's even cool is some of the cross-training stuff, it will potentially do it in your own tone, in your own language. By understanding how you use words, it could be actually much more personable to how you talk as well, which is awesome. So not far away, Steve, at all. This is stuff that you already see, already published in papers, already happening in the labs, and in some cases even happening in a small trial.
That's great. It's a great time to be alive and waiting for this to happen. I have one audience member coming up here.
Yeah, good to see you, Stevie. This is Jongso.
Jongso, what's up?
Yeah, what's up? Yeah, there's a lot of new things. Yeah, I'm happy to be here. Anyway, I have a question. Since you have a very, very lots of interesting project, what about the metaverse related stuff? I haven't seen it. Do you have any plan?
Jongso, did Jeff Allen ask you to ask that question?
Oh, really? No. Okay, so anything, I don't know. Just go ahead.
At Microsoft, we've been working on VR for quite some time through the HoloLens effort there. I would say that there's a lot of exciting things that can happen outside the metaverse just as well as inside the metaverse. I'm really excited and focused on the stuff that's happening outside the metaverse. I think that it's for me, it's highly tangible, no pun intended. It's highly tangible. I can see it in the computers and devices that we build today. I can influence the computers and devices that we're working on. I think there's going to be, a whole category of new devices that are yet to be invented that I want to go invent. And, I would say that there's a lot of smart people thinking about how to do that in the metaverse, and that's great. They should go do that. But I think that there's a whole bunch of other really interesting things that I want to go figure out.
Okay, thank you, and see you. Hope to see you soon. Bye. Thank you.
Thanks, Jung So.
Okay, Stevie, we have one last question, and then we're going to let you go. Go ahead, sir.
Hi, this is Ludatic. I have a philosophical questions for you because I was wondering whether you have any opinion about the fact that people bat around the term artificial intelligence about everything, as opposed to saying imitation intelligence or computationally assisted statistical inference. You know, how do you define what really is intelligence?
That's a great question. That's a wonderful question. I think right now, people use it to reference an entire body, an entire emerging field, or been emerging for quite some time, that uses these mathematical techniques and these deep neural structures to implement an algorithm that in many ways seems to manifest intelligence. But you're kind of right in so many ways. Is it actually, it's not conscious, and therefore maybe not that really intelligent. It just is something that is designed to do something that you've trained it well, and it'll execute this algorithm and it'll do it well. And by the way, if you give it a data set or an input that is outside the scope of the data that it was trained on, oftentimes you see AI or these models essentially fail. And that's quite different than what intelligent beings do. They're able to adapt and learn. Now maybe fields like reinforcement learning will come into play here and help our models evolve by themselves, but you don't see that today. But absolutely, I think the thing to say is that these are algorithms designed by humans, and they're in the scope of human control, and they do something really well as a result of human activity and nothing more.
Thank you, Stevie, so much for giving us your time this afternoon. We're going to give you a big round of applause, even if you can't hear it from outside the microphone. Have a wonderful day.
Thank you, folks. That was a lot of fun. And sorry, next year I'll be there in person, I hope. Thank you so much.